Today we are going to discuss about another use case that is regarding the capacity planning of a generative AI platform. It is very interesting. A lot of things we need to discuss, and while we are planning a generative AI kind of platform, it's not like the previous WhatsApp or YouTube. There are concept of token comes into picture, a lot of other parameters we need to consider. Let's go deep dive into the capacity planning of generative AI platform. This is a part of the system design of any kind of such platform. Okay, first part, I'm going to discuss few details about this capacity planning, what we are going to do. All these things are listed in this README file. Then I will go ahead with the glossary, and then we'll do the capacity planning, and finally we'll do some model comparison. Now let's divide them into four major categories. One is called the user load, the second one is called the performance, third one is hardware requirement, and the optimization. In user load we have around 11 parameters we need to consider, just like a daily average users, prompt, token, input tokens, output tokens, request per second, peak factor, concurrency rate, replication factor, break-even point, and 80-20 rule. Regarding the performance, when we consider, we need to think about TPS. TPS means token per second, key value cache, that is semantic cache, API gateway, and vector databases. Regarding the hardware, we have around 5 parameters need to consider. That's VRAM. Then come to the GPU inferencing engine, that is A100 80 GB and S100 80 GB. Next come to the GBPS and tensor parallelism. And regarding the optimization, we can use VLLM and continuous batching, quantization, and retrieval augmented generation. These are the things we are considering while doing the generative AI platform capacity planning. Let's go deep into one by one, and we will see what are the equations, how we can calculate them. First thing, the user load metrics. The first and foremost one is daily average users. Okay, that is a unique users interacting with the system in one day. Okay, that we consider, if we consider ChatGPT, it's around 100 million users are interacting with the ChatGPT platform daily. Enterprise SaaS platform, we can consider around 10K to 500K. As a starting point. Okay, prompt. Prompt means a single user request to the LLM, including that include the system prompt, user messages, etc. Each prompt generate one input token and uh, one input token group and one output token group. Token means the smallest unit of text processed is called the token. It is called the token. The smallest unit of text processed by LLM is called the token. One word means 1.3 times tokens. If we consider like that, 1 KB of text means 250 tokens. In that context, one page means around 500 tokens. And input tokens in the prompt, send it to the model. That is a system prompt plus user message plus context. Typically for chat, it will be 200 to 1000 tokens. If it is a retrieval augmented generation, it will be 1000 to 400 tokens. If it's a long document, it will be 10,000 plus documents. Okay, output tokens in the model's generated response is called the output tokens. Usually for short Q&A, it will be 550 to 200. If it is a code generation, it can range from 200 to 1000. It's a long reasoning models and all, then it will be 1000 to 4000 tokens. RPS, request per second. Request per second, it's a prompt level throughput. RPS is prompt per day divided by number of seconds in a day. Okay. Next, come to the peak factor. Peak factor means the ratio peak hour traffic to the daily average traffic. That is, consumer apps, we will be considering 2 to 3 times the daily average. Okay, live events and all we can consider 5 to 10 times. Concurrency rate, that's a fraction of daily average users active simultaneously. That is called the concurrency rate. Okay, typically 3 to 8% of the consumer chat application we can consider as a what concurrency rate. 3 to 8% of the consumer chat app. Next, come to the replication factor. Usually for the redundancy, we keep 3 replica, 1 active, that is 1 primary, and 2 replica. A break-even point, that means the token volume at which the self-hosting is cheaper than the API. That is called the break-even point. Typically, 500 million tokens per month for A100 GPT to 2 billion token per month for H100. 80-20 rule, that means 20% of the data are the 80% of the requests. That is called the 80-20 rule. We use this for the caching. Next, come to the capacity planning for the performance metrics. While we consider about the performance metrics, we need to consider the token per second is the first parameter. Okay, that is a throughput measure for LLM inference. TPS is daily tokens divided by number of seconds per day. You will get the token per second. Next, come to the key value cache. Key value cache storing the intermediate attention state during the generation. Okay, that will add up 20% of the VRAM requirement. VRAM, I'm going to discuss what is VRAM and all in the upcoming slides. Okay, formula that we can use around 1.2 times multiplier. Sorry, we can use 1.2 times multiplier as the formula. That is, suppose if you have the initial requirement of around 20 GB, 10 GB RAM, we need to consider about 12 GB. That is 1.2 times the virtual video RAM. VRAM is video RAM. Then semantic cache, caching the LLM response by semantic similarity of the queries. That is, this similarity cache is going to reduce the cost. Okay, we are going to cache 30% of the hit rate, 30% of the cost reduction with the zero latency. Whereas this KV cache is going to increase the cost. API gateway, entry point for all the API requests. It handles the authentication, rail limiting, and routing. We can use Kong, AWS, API gateway, or vector databases. Database optimized for similarity size for on high dimensional embeddings. So we can use Pine, Quadrant, Wave8, Melvis, etc. Our size calculation is vector into dimension into 4 base. That is how we are calculating the size of the vector DB we need. Next, come to the capacity planning of hardware metrics. When we consider about the inferencing of this GPT kind of model, the major things is video RAM. Video RAM is not like the system RAM that is going to reside in the motherboard. We're going to discuss in detail about the video RAM later. This video RAM on GPU must hold are the full model weight and KV cache. A100 is 80 GB video RAM. H100 is 80 GB video RAM. H100 NVL 188 GB video RAM. The A100 can handle around 800 token per second. That is FP16 70 billion. The cloud cost is around $2.50 to $3.50 per hour. Whereas H100 it's around 3 to 4 times. That is 2,400 token per second it can handle at the same. And cost is little bit higher, around $4 to $6 per hour. And GBPS, how we are calculating the GBPS, and tensor parallelism, that is splitting model layers across multiple GPU, that is called the tensor parallelism. Minimum GPU required is C of VRAM needed divided by GPU VRAM. I am going to discuss this in detail while we are doing the capacity planning. Let's come to the optimization metrics. Okay, VLLM, that is high performance LLM serving framework with continuous batching. That is 5 to 10 times the throughput versus nav serving. That is the industry standard. Dynamically improves the GPU utilization. Quantization, reducing the model weight. Okay, F16 int 8 it will half the usage of VRAM. F16 int 4 it will quarter the usage of VRAM without reducing the quality of the output. RAG, that is retrieval augmented generation, that is fetching relevant doc before prompting. Okay, a require vector database, add latency, but reduces the hallucination of the results. Next, go to the capacity planning. Before capacity planning, I just want to discuss few things which I have shown you that I said we are going to discuss about these parameters. One is minimum GPU requirement. There is an equation called CL of versus VRAM needed divided by GPU VRAM. What does it mean? Okay. Each parameter minimum GPU, there is a minimum number of GPU cards required to run the model. VRAM, that is a video RAM, that is a total GPU memory your model required. That is model weight plus KV cache plus activation functions requirement. GPU RAM, memory capacity of the single GPU card, that is A100 is having 80 GB, H100 is having 80 GB video card. And that we need to do, that is how much GPU worth for the memory unit. Seal means rounding up to the top. Why we are using seal instead of round and floor? These are the other rounding parameters we can use. Suppose if we need the VRAM requirement is around 90 GB and GPU VRAM is around 80 GB. If we consider divide 90 GB divided by 80, we will get around 1.125. But we cannot go and purchase 1.125 GPU. Instead, we can go for the upper limit, that is 2. Okay, I cannot floor. If we take the floor, it will be going down. It will consider rounded into 1. If we round, then again it will be rounded back to 1. If it is seal, if it is 1.125, it will rounded to 2. That is safe enough VRAM to load the model. We'll get enough space to run the model. Okay. Let's see some examples. Suppose our VRAM requirement is 160 GB. Single GPU VRAM is 80 GB for A100. So minimum GPU required is we can take the seal of 160 divided by 80. That means seal of 2. That means 2 GPUs we need. That is for this is even calculation. If it is uneven division, that is model VRAM required is 170 GB and the single GPU VRAM is 80 GB. So if you consider that one, seal of 170 divided by 80, we can get a seal of 2.125. In that case, we need to consider to the next upper level around it. That is 3 GPUs we need. Next, think about the small model that fits on 1 GPU. Model VRAM requirement is 14 GB. Single GPU VRAM is 24 GB. Around this RTS 3090. Minimum GPU requirement is seal of 14 by 24. That is seal of 0.583. We can consider as 1 GPU. Okay. This is how this visual intuition, that is VRAM required is 200 GB, GPU VRAM is 80 GB. The first GPU will consider take the first 80 GB, second GPU will take the second 80 GB, third GPU will consider only the remaining 40. Okay, still needed, but here still we need the full GPU because we cannot divide the GPU and give it to some other process. Total requirement is 3 GPU. Okay. The nutshell is the divide your total memory needed by what 1 GPU can hold. Okay, then always round up because you can never use the fraction of a GPU. You have to consider the full GPU for inferencing. So, okay, next come to the VRAM. We have seen the requirement of VRAM many places in our architecture. This is not architecture. Capacity planning design. So what is meant by VRAM? VRAM is the video random access memory. Okay, VRAM is the dedicated memory built directly onto the GPU card. No, it's not like the RAM. It is very fast as it is sitting in the along with the GPU card. It is a separate from your system RAM and is used exclusively by the GPU to store everything it needs to do its work. Okay, so if you see the analogy, our disk or system RAM store everything your computer needs, whereas VRAM is hold what this GPU is actually working on. It will be like a weight you can consider, then key value cache you can consider, such kind of parameters it is holding. The system RAM is large but far away, and the VRAM is small but right next to the GPU, and it is extremely faster. Okay, what gets stored on VRAM? These are the content it is stored on the VRAM. One is model weight, key value cache, activation functions, input output buffer, and textures and frames. Okay, these are for the gaming and 3D graphics. It is saying the textures and frames in that VRAM. In our cases, these are the parameters it is said, that is model weights, key value cache, activations, and input output buffers. And why the VRAM matters for AI and LLM. Okay, GPT-3, it's around 175 billion parameters. It's around 350 GB VRAM is required. We need multiple A100 GPUs. Llama 3, it's around 70 billion parameters. We need around 140 GB of VRAM requirement. We need two A100 GPU. 80 GB GPUs. Llama 3, it's 8 billion parameters. We need 16 GB of VRAM and fits in one RTX 3090 GPU. What it means is if the model doesn't fit the VRAM, it won't run. That's the problem. So this is how we are calculating minimum GPU requirement is zero video RAM requirement divided by total GPU virtual video RAM. Okay, these are the comparison. RTX 4090, it is around VRAM is 24 GB. A100 is we have 40 and 80 GB variants are available. H100 it's 80 GB. H200 is 141 GB. This is for the frontier LLM inference we are using. Okay, this is what this um, two things we said we are going to discuss later. One is what is meant by VRAM, and the other one is the equation to calculate how much RAM is VRAM is required. Let's close this one and go to the capacity planning. Okay, this is the capacity planning. We can divide into different sections. Section A, we are going to do the assumptions. Based on these assumptions, we are going to calculate the following parameters. Second is the daily throughput metrics. We are going to calculate how much is the daily throughput. Section C, the LLM inference and GPU sizing. And section D is the API and gateway infrastructure we require. Section E is vector database or RAG system we need to consider. Section F is now monthly cost estimation. Next come to the future scale, that is the projection. What will be the next 3 year or 5 year or 10 year? Okay, 10-year calculation. No, it is not done. It's just a multiplier of 1 year. Let's see one by one. The first thing is assumptions. What are the assumptions we are going to take for doing the capacity planning? First thing is daily average usage or DAU. We are considering around 50K usage as the daily average usage. Okay, prompt per user per day. We are expecting one user is going to do 10 prompt per user per day. That is 10 prompt each user is going to do every day in an average. Average input tokens per prompt, around 512 tokens we are expecting for average input. Okay, that average input token per prompt. Per prompt, we are expecting around 512 tokens. Okay, that is the sum of context, system prompt, user message. Okay, one word means 1.3 times tokens. Then average output token per prompt, that is 256 tokens. LLM response length, that is the LLM response length. Okay, if it is a short answer Q8 kind of thing, that is 100. Or long term, we can consider around 1000 or above 1000. Next, come to the read write ratio, that is read per one write. That's we are considering it as 3 as a ratio. Read of prior message versus new writes. That is what the read write. Typical chat is around 3:1. Peak to average traffic factor, we are considering 3 as the traffic factor. At peak level, we can consider around 3 times of the normal traffic. Concurrent user rate, that is around 0.05 is the concurrent user rate we are using. Concurrent user is how many users are at a time using this platform. Model size, that is in billion parameters, we are considering 70 billion parameters. That is 100 billion parameters. Llama 370 billion, GPT 3.5, GPT-4 classes. These are all 70 billion parameters. Model precision, that is 2 bytes per parameter. That is a model precision we are considering. That is F16 is a 2. That is indate 1, F32 4, F16 is the standard inference default. A GPU VRAM requirement, that is 80 GB we are considering as a video RAM. Then GPU cloud rate, this we are expecting around $2.50 per hour. That is for the A100. It is H100. It will be ranging from $4 to $6 per hour. API token price, we are considering $2.50 per 1 million token. And API token price for the output, that is for the input, but for the output, it will be a little bit higher. It's a starting range, it will be around $10 per 1 million token. If you see in the vector databases and all, not the vector database, in the RAG system and all, we have this embedding is there and generation is there. Yeah, for the embedding, cost will be very less, but as compared to the embedding, the generation cost will be very high. That is what the difference between input and output tokens. Cache hit rate, we are expecting around 30% of the requests hit the cache. Remaining will be cache miss. It has to go to the origin, or it has to go back to the LLM model and get the data. There is a semantic cache reduce effective of API calls. 30% is the realistic target. Data retention period is 2 years. We are considering to keep the user data and their queries and their metadata for the 2 year. After that, the data and the metadata will be removed. That is how long the conversation history and the embeddings are retained. Our replication factor, we are considering 3 times the replication factor for redundancy. And seconds per day, that is 86,400 as a seconds per day, and it's not going to change. And based on that, these are the daily throughput. Daily average usage, 50,000 we have seen earlier. And prompt per day, how we are calculating the prompt per day, daily average user into prompt per user. Prompt per user, we have considered it as 10 prompt per user per day. So therefore, the prompt per day is around 10 times the daily active usage, that is 500k. Based on that, we can consider total token per day. Total tokens per day, daily average user into prompt per user, the previous calculation, that has to be multiplied by the sum of input and output tokens. Sum of input and output tokens, if you see, this is the sum of input and output. 512 plus 256 is the input and output tokens. That we will get around 384 million tokens per day. That is a total token per day. For the input tokens, we need to consider DAU, daily average user, into prompt per user into average input tokens. Okay. Similarly, if you're considering the output token per day, we need, instead of this input token, we need to consider the average output tokens. These are simple mathematics. It's already given here. What are the input tokens? What are the output tokens and all? And based on that, we can calculate the what total token per day, input token per day, and output token per day. Then we can consider the token per from day. It is the 24-hour calculation. If you consider to calculate the token per second, we need to divide by 86,400. Average token per second, that is TPS, that is around 4K, that is 4,444K. How we are getting token per second? We are total token per day divided by 86,400. We will get around this value. Peak token means we have to consider multiply that value into 3 times. That is 3 times 3 is the peak factor. We will get around 13,333 token per second. Average request per second, that is RPC, 6 requests per second, that is prompt per day divided by 86,400. Where is the prompt per day? Prompt per day total, we need to consider total prompt per day. Where is it? Prompt per day. This is the prompt per day. That is around 500k divided by 86,400. We will get around 6. Then peak request per second, that is around 17. How we are getting? Average request per second. Where is average request per second is 6 into peak factor. That means peak factor is 3. Around, it should be around 18. It should be around 3 times. Let's check what factor we have taken. Peak to average traffic factor is 3 times. It should be not 17, it should be 18. It will be there. It's not a big change. Concurrent users means how many users are currently simultaneously using that platform. That we can calculate using daily average users into concurrency rate. And the concurrency rate we have considered here as 0.05 is the concurrent user rate. So if you consider to multiply daily average users into concurrency rate, we will get around 2,500 users. Now read RPS, that is 4 requests per second, and write RPS is 1 request per second. How we are calculating? Peak RPS into read share. and peak RPS into right share, we will get the right RPS. And effective prompt after the cache, it will be 3000, 350K prompts per day. How we are getting this one? Prompt that actually hit the LLM after the cache hits. If we are considering 500K as the prompt per day, we need to consider only 30% of them are cache hit, remaining are cache miss. That means 30%, 1,50,000 is a cache hit that we are get the result from the cache server ready for some other. Hello everyone, this is Arif here. Today we are going to discuss about another use case that is regarding the capacity planning of a generative AI platform. And is very interesting. A lot of things we need to discuss, and apart from that, I'm going to discuss few more. Okay, and there are a lot of terminologies we need to discuss while we are planning a generative AI kind of platform. It's not like the previous WhatsApp or YouTube. There are concept of token comes into picture, a lot of other parameters we need to consider. Let's deep dive into this architecture design, not the architecture design only. Um, Capacity planning for generative AI platform. Okay, let's go deep dive into the capacity planning of generative AI platform. This is a part of the system design of any kind of such platform. Okay, so first away, so okay, first part, I'm going to discuss few details about this capacity planning, what we are going to do. All these things are listed in this README file. Then I will go ahead with the glossary, and then we'll do the capacity planning, and finally we'll do some model comparison. Okay, now let's see what we're going to do on this capacity plan. Okay. Cache server. The rest 3,50,000, that is 350K, it has to go to the origin server and fetch the details. That's called the cache miss. Okay. Next, come to the LLM inference and GPU sizing. Model VRAM requirement is around 168 GB. That is a parameter, and into bytes per parameter into 1.2 kV cache overhead. Minimum GPU we are required is sorry. Minimum GPUs required is around 3 GPU. This is we are using around A100, that is 80 GB. If you consider to divide 160 by 80, we will get around, we need around 3 GPUs. We are taking the seal of that calculation. Recommended GPUs with the hard room around 6 GB, that is minimum GPU into 2, that is for batching, redundancy, and KV growth. We need to consider 2 times. And tensor parallel size is 3. How we are getting number of GPU per model replica, that is minimum GPU required. We are considering 3 as the 3. And tensor per second for a 100 GPU, it's around 800 token per second is the tensor. GPU cluster required, that is 3 clusters. That is how we are calculating seal of peak token per second divided by TPS per GPU into GPU per cluster. Total GPU required, that is 18 GPUs required, that is cluster into GPU per cluster. We will get the total GPU required. Monthly GPU, that is monthly GPU cost, that is around $32,850. How we are calculating? Total GPU required into cost cloud, how many dollar per hour into 370 hour, that is the in 1 month how many hours are there, we need to multiply with the how many hours, that will give the monthly GPU cost. And video RAM utilization target is 11.7% of the pool, that is model VRAM divided by total provision VRAM. We will get the VRAM utilization target. Let's come to the API and gateway infrastructure we require. A gateway request per second average 6 requests per second. It is passing through the average prompt RPS. And gateway RPS is that is the peak and design. 17 requests per second is the peak gateway RPS. And average request payload is 1 KB. that is input plus output into 1.3 times the token divided by 1000. We will get the average request payload in KB. Average bandwidth required, that is 0.01 MB per second. How we are getting a request in KB into gateway average RPS divided by 1000. We will get this bandwidth in MB. And peak bandwidth required, that will be we need to consider the 3 times. If you consider in GBps, it will be very small. Daily storage growth, that will be 499 million bytes per second. How we are calculating? Prompt per day into total tokens into 1.3 times bytes per token. This is how we are calculating the daily storage requirement. This is in bytes per day. Daily storage growth in GB, if you convert this into GB, it's around 0.5 GB per day. That is bytes divided by 10 to 9, we will get the value in GB. Okay. Yearly storage growth in terabyte, we need to convert into GB, 0.5 GB per day into 365 divided by 1000. We will get value in terabyte. That is 0.18 terabyte per year. Total database storage required is, we need to consider many factors while you're considering the databases and all. Yearly storage in terabyte into retention per year and replication factor. Replication factor, usually it will be 3 times the replication factor. Then how many years we need to retain this data, that also need to consider. Multiply all of them, we will get around 1.09 terabyte. And cache requirement, it's almost the same. 7-day rolling window and cache hit rate, that is the total hot RAM required from the cache server. Next, come to the vector database. Vector database we use for retrieval augmented generation. Embedding per user, we are considering around 500 vector per user. Total vector in the index is around 25 million vectors. That is daily average user in embedding per user. That is Pinecone P1 handles around 1 billion records at a time. Next thing is vector dimensions. We have this 1536 dimensions. That is OpenAI text embedding 3 small. We can next go to the indexing size in GB. It's around 153 GB is the embedding index size. How we are calculating vectors in dimension into 4 bytes. That we will get the index size. How to calculate the vector query RPS? That is, we already have the request per second. That is 6 requests per second. That is each prompt trigger a vector similarity size. Vector query request per second, that is peak RPS. That will be around 17. That is 3 times the request per second. That is 17 requests per second. Peak RPS equal to same as LLM peak. That is vector DB must handle this pressure. Monthly vector database cost, it will be around $215 per month. Next, come to the monthly cost estimation. This is going to be the crucial part. Based on this calculation, our total monthly cost will come. Okay, so yeah, why this mouse is so crazy, I don't know. Okay, monthly token, we are expecting around 11 billion token per month. Okay, daily tokens into 30 days, we will get the monthly token. Monthly input tokens, that is daily input tokens into 30, we will get the monthly input tokens. And monthly output token, that is daily output tokens into 30, we will get the monthly output token. Effective tokens, that is 8 billion. How we are getting total monthly tokens into 1 minus cash hit, that will give the effective tokens after the cash. We don't need to consider the cash because it is not going to this cash. Around 30% of them is not going to hit the origin server because we already have the data residing in the cache server. It can fetch the data from the cache server instead of going to the LLM model. Okay, API cost, we are expecting around $13,440. That is input token divided by 1 million into input price. Okay, multiplied by 1 minus cash. There also we are reducing the cache server. That is 30% of the data residing in the cache. So we don't need to consider them to calculate the monthly cost. API cost, that is around 38,400. How we are getting output token per 1 million. 1 million requests into output price. Okay, total API cost will be the sum of these two, input plus output API cost. And self-host, suppose if you are considering a an self-hosted LLM model, then we can reduce to 32,850 from 51,000. This is for the hosted one, that is a cloud hosted one, or vendor locking is there. Here, if you are hosting ourselves, the cost can be reduced to 32,850 from section C. Total CPU cluster monthly cost. Here we need to consider to handle all the GPUs and all by ourselves. API gateway cost, that is around $350 per month. Vector DB cost is around 215 vector DB cost. Redis cache cost is around $200. Object storage is around $4 per month. Observability and monitoring $300. That is for Grafana, Cloud, Langsmith, Prometheus, typically around $300 to $800 per month. Total API base per month is around $52,909. That is for the API base. If it is a self-hosted, that is around 33,919. That is for the self-hosted GPU stack monthly total. And monthly savings, if you are using self-hosted, around monthly we can save around $18,000. Cost per 1K prompt, which is coming at around 105.8187 per 1K prompt. And this is all about our monthly cost estimation. Next, go to the future scale. Future scale, we have received the initial cost analysis, and or we have identified how much will be the capacity. Based on that capacity, we have identified how much it will be the monthly cost and all. If you multiply it to 3, we'll get the next 3-year plan. And if you multiply with 5, that will be the 5th year forecasting or projection. It can vary because if the usage is increasing tremendously, then it can vary based on that. This is all about the capacity planning of any generative AI kind of platform at scale. And let's go ahead and see few model comparison. Okay, LLM model comparison, APA versus open source pricing as of 2025. I have collected these details from our OpenAI and Claude models, chat models. I collected this information. Okay, let's see. Initially, there are 4 models, that is GPT-4o, GPT-4o mini, GPT 4.1, and O1, O3. These are all from OpenAI. Context window sizes 4o and 4o mini is 128K. GPT 4.1 context window is 1 million. O3 and O1 it's around 200K. And for input for 1 million cost, for GPT-4o 2.50. For GPT-4o mini, it's well less. It's $0.15 per 1 million. GPT 4.1 input is $2. Is less than the GPT-4o. Whereas O1, O3 input token cost is $15. It's very high. Okay. Output token, GPT-4 is $10 per 1 million token. GPT-4o mini, it's 0.60. That's well less. GPT 4.1, it's around $8 per 1 million token output, whereas in O3, O1 or O3, output token for 1 million is $60 per 1 million. That's very high. And speed, when we consider speed, 4o is fast, 4.1 is very fast. GPT-4o mini is very fast because that's a small model, and 4.1 is fast, and O1 and O3 is slow. These are the condensation used, that is FP16, and these are the usage of those model. If you are using GPT-4, we can use for general purpose vision, coding, agent, and all. For our mini, we can use high volume, cost sensitive tasks. Then GPT 4.1 we can use for long context, coding, and reasoning, and that is a little bit costly. On or O3 we can use for complex reasoning model, math and science we can use for on or O3. Next, come to the few models from Claude. 2 models from Claude, that is Claude Sonnet 4.6 and Haiku 4.5. This is from Anthropic. Context window is 200K only. Input token cost is $3 per 1 million token from Sonnet 4.6 for way less in HeyQ 4.5, that is 0.80 per 1 million token. Whereas come to the output is way high. Sonnet 4.6 is costing around $15 per 1 million token and $4 for HeyQ 4.5. As compared to the speed, Sonnet is fast, HeyQ is small model, it's very fast. The same condensation method we're using FP16, and usage is Sonnet 4.6 we can use for long documents and coding, deep analysis and all. HeyQ 4.5 for summarization, classification, retrieval, augmented generations and all. And Gemini next come from Google, that is Gemini 1.5 Flash and Gemini 1.5 Pro. The most advantage here is the context window is very high. If you see the Flash, it is 1 million is the context window, that is very high as compared to the previous model. But GPT 4.1 is giving a 1 million token. But the cost, if you see the input for 1 million token and output for 1 million token, the cost is very high for the OpenAI models. Whereas in Gemini for 1 million token, we are getting around $0.075 per 1 million token. That is way less as compared to the any of the previous model. And for the output also, it's costing only $0.30 per 1 million. It's very fast. Same condensation, you can use 1 million context multi-model, and it is very low cost. If we go ahead with the Gemini 1.5 Pro, 1.5 Pro, that is giving double the context window of Flash, and it is cost is little bit high as compared to the Gemini 1.5 Flash, but it's not too much high as compared to the previous one, that is $1.25, and the output is $5 per 1 million token output. And speed, as compared to the previous one, speed is medium, same condensation, but we can use it for ultra long context and RAG retrieval augmented generation, RAG retrieval section we can use this one. These are all deployment is only AP only, because these are all hosted on the vendor locking. These are hosted on the vendor side, and there is a vendor locking for this API. So if we need to consider to reduce the cost, and if we can bear the cost of GPU by yourself, then we can go ahead with the self-hosted. We can host, if you have the GPU models and all, we can do the inferencing by yourself. Then consider about the self-hosted one. The advantage of self-hosted one is there is no cost for input and output tokens. Okay. And there is some limitation for the context window also. Okay. And there are different condensation methods available to reduce the size of the inferencing models. We have three from Llama, that is Llama 3.18 billion, Llama 3.170 billion, Llama 3.1 405 billion by Meta. And the context window is 128K, and there is no cost associated with the self-hosted for input or output. Llama 3.1 is fast, 3.170 billion is medium speed, and 3.1 405 billion parameter, that is slow. Even though the quantization method we are using here is int4 to int 8. For the Llama 3.1, we are using FP16 to FP16 or int 8. Llama 3.1 405 billion is int 4 and FP16. So Llama 3.1 we can use for high volume, privacy, and edge deployment. And 3.170 billion we can use for GPT 3.5 parity and on-prem or fine-tune model. And 3.140 billion for 405 billion we can use for GPT-4 parity and full control and hip hop. Okay. Next, come to the model from Mistral. That is two models from Mistral, that is 7 billion and 8 into 7 billion. Context is way too less, that is only 32K. These are very fast, lightweight reasoning and fast inference. Mistral of expert, that is GPT 3.5 quality at lower compute for the Mistral 8 into 7 billion. Then come to the Quint 2.5 72 billion from Alibaba. Context window is around 128K. No cost associated with that. Medium speed. and quantization uses FP16 or Int8. It's a multilingual model, strong coding and math, as well as very good as compared to other models, because I have used it especially for coding and all. And DeepSeek R170 billion is from the DeepSeek, that is 64K. This is the context window. It's a little bit slow as compared to the other models. Mm, we can use this for chain of COT, chain of thought reasoning, and researches and all. Okay, these are all about this comparison wise. If we consider the OpenAI API versus open source dimension framework. This is all about how we can do the capacity planning as a part of the system design for any of the generative AI platform. I hope you have enjoyed this video, and I hope you got what I have explained with respect to this calculations and all. That's it as of now. I will come up with some other use case also in the upcoming days. Stay tuned. Have a good day. Bye.